Hello and welcome to Medical Dialogues. I'm Anshika Mishra. Let's look at today's top medical news. Scientists create microscopic robots that navigate blood vessels to treat strokes. Stroke affects 12 million people worldwide each year, often causing death or lasting disability. Now, current treatments use high dose of clot-dissolving drugs that spread throughout the entire body, leading to serious side effects like internal bleeding. However, research at the ETH Zurich have developed a groundbreaking microbot to deliver these drugs directly to the stroke-causing clot, minimizing systemic risk and improving precision. The microbot consists of a tiny spherical capsule made of a soluble gel shell containing iron oxide nanoparticles that give it magnetic properties. These nanoparticles allow the capsule to be guided inside the body using an electromagnetic navigation system. Now, the capsule is injected via a special catheter into the bloodstream or cerebrospinal fluid, then precisely steered to the thrombus and three distinct magnetic navigation systems, enabling it to navigate complex brain vessel network at a speed of up to 4 mm per second, even swimming against blood flow exceeding 20 cm per second. Now, the gel capsule also contains the therapeutic agents such as clot-dissolving drug, which is released upon application of a high-frequency magnetic field that heats the nanoparticle, dissolving the capsule and freeing the medication exactly where it is needed. Researchers validated this approach through extensive trial using realistic silicon vessel model and animal tests, achieving drug delivery success in over 95% of cases. Now, this innovative microbot system represents a major advance in targeted, minimally invasive stroke therapy and holds promise for treating other localized conditions like infection and tumors. Its development merges robotics, material sciences, and medicine, heralding a new era in precision healthcare. Now, the team is now focused on moving rapidly toward human clinical trial to bring this technology into operating rooms globally with the goal of improving outcomes and offering new hope to stroke patients. Study finds high-protein breakfast boost fullness but do not change how much you eat later. A new study from Newcastle University explores whether plant-based protein can rival animal-based protein in curbing hunger after breakfast. With growing concerns about sustainability and ethics, this research published in European Journal of Nutrition addresses whether plant and animal proteins differ in their ability to suppress appetite and influence subsequent calorie intake. Protein is essential for health, but environmental and ethical concerns have increased interest in plant-based alternatives. Protein impacts digestion, metabolism, and appetite by stimulating satiety hormones like PYY and GLP-1 while suppressing ghrelin. Studies showed variety results. Some find certain plant protein more satisfying, others favor whey. Liquids generally suppress appetite less than solids, but the influence of protein sources on this difference remains unclear. The research involved 18 healthy adults in a randomized crossover design. Participants consumed 3 breakfast types on separate occasions: a plant-based high-protein drink, an animal-based high-protein meal, and a low-protein high-carb meal. After fasting overnight and avoiding caffeine and exercise, they consumed the breakfast under controlled lab conditions. Appetite was assessed using visual and analog scales for 4 hours, and blood samples were collected to measure satiety hormone, peptide YY, and glucagon-like peptide 1. Finally, participants ate an ad libitum lunch to test how breakfast affected later food intake. Results showed both high-protein breakfast significantly boosted PYY and GLP-1 level compared to the low-protein meal, with no meaningful difference between plant and animal-based proteins. Subjective appetite decreased more after the plant-based drink, though differences were modest. Importantly, calorie intake at lunch did not differ across breakfast types or age groups. Hormone levels correlated weakly and non-significantly with energy intake. Now, the study concludes that plant-based protein drink can match animal-based meals in stimulating satiety hormones and reducing appetite, offering a practical, sustainable breakfast option. However, these hormonal and appetite differences did not translate into decreased food intake later. Limitations include the small older adult sample and lack of testing different meal forms. User research should examine long-term adherence and real-world effect. Now, this work supports plant protein as effective alternatives to animal sources for appetite control, aligning sustainability and nutrition goals without compromising satiety. Study finds hidden immune cells in brain may regulate anxiety levels. New research from the University of Utah reveals that 2 distinct groups of immune cells in the brain, called microglia, have opposing roles in regulating anxiety. Unlike neurons, which transmit signals, microglia act as an anxiety accelerator and brake. One subset, non-HOXB8 microglia, increases anxious behavior like repetitive grooming and avoidance, while HOXB8 microglia reduces anxiety and counterbalance this effect. Anxiety disorder affects over 300 million people worldwide and represent one of the fastest growing mental health challenges globally. Factors such as increased stress, urbanization, and social isolation contribute to its rising prevalence. Despite its commonality, many cases remain undiagnosed or untreated, highlighting an urgent need for improved awareness and interventions. Now, anxiety affects the brain by overacting the amygdala, which processes fear and emotion, and impairing the prefrontal cortex responsible for regulation and decision making. Chronic anxiety leads to structural and functional changes in this area, disrupting emotional control and increasing stress sensitivity. Now, this can result in difficulties with focus, memory, and emotional regulation. To study this, researchers transplanted each microglial type separately into mice that lacked these cells. Mice receiving only non-HOXB8 microglia showed heightened anxiety behavior, while those with HOXB8 microglia acted normally. Importantly, mice with both microglial types displayed balanced anxiety levels, showing these cells work together to regulate anxiety precisely. Now, these findings challenge the traditional view that anxiety is mainly controlled by neurons, highlighting the immune system's crucial role in brain function and mental health. It also opens the door to novel treatment focusing on microglia to either enhance their calming effect or inhibit the anxiety-promoting activity. Since humans also have this microglial population, this discovery could lead to more targeted therapies for anxiety disorder in the future, moving beyond current psychiatric drugs that primarily treat neurons. Though clinical applications are still forthcoming, this study marks a major shift in understanding and potentially treating anxiety by modulating the brain's immune cell rather than just the neural circuits. Thank you for watching. Stay tuned to Medical Dialogues for more updates.
Never miss a medical update from Medical Dialogues. Like, subscribe, and press the bell icon.